Hello, my name is Mark, and I'm going to tell you a little bit about the project I did as my final project in the class CS 350C Advanced Computer Architecture this semester. My project is called MarkMusic. My goal was to find a way to encode sheet music in a way such that it can be read by the FPGA board that we've been using all semester for our projects. And to do so, not only did I have to work with the sound drivers on the board, but I invented my own instruction set for encoding the sheet music, wrote an assembler for that instruction set, and then wrote the Verilog to interpret that instruction set and run two voices in parallel on the board and produce the output to the audio on the board. All total, this project, including encoding the music, was probably about 40 hours of work over the past 2 weeks. So first I'm going to tell you a little bit about the instruction set that I invented. So all of my instructions are encoded as 16-bit instructions stored in the memory file. I've got two basic types of instructions that are determined by the high order bit. If the high order bit is a 0, the instruction is interpreted as a note. If the high order bit is a 1, it is interpreted as another kind of instruction. The notes are encoded as follows. High order bit is a 0. The next 5 bits determine the duration of the note in terms of 16th notes, eighth notes, quarter notes, half notes, and whole notes, and they add up. So if you have a half note and a quarter note, if you have a 1 in this bit and this bit, it will add up those two values to determine the duration of the note. This allows for things such as tied notes, dotted notes, and other strange rhythms. If all of these bits are 0, essentially a no duration, what you get is a grace note which takes up 1/16 or 1/8 of a 16th note's time from the next note that is being played. In music, a grace note is a very quick note that comes right before another note is played and takes away time from that note. Okay, the next 3 bits are the volume bits. On a scale of 1 to 7, 1 being pianissimo, 7 being fortissimo, which is the loudest that you can play. A volume of 0 determines a rest, so whatever duration is listed here, if the volume is a 0, the board produces no sound and does not play any other notes for that duration. The next 3 bits are the octave of the note. Notes in music are divided into octaves running from 0 up to generally 7, and each C determines an octave. Middle C is C3. The C one octave above that is C4, and so on. And each note after that C is considered to be in the same octave as that C. So these 3 bits determine which octave from 0 to 8, and that encompasses, 0 to 7, and that encompasses basically the range of a standard grand piano. So any note from a grand piano almost can be played with this instruction set. And then the final 4 bits are the pitch of the note, encoded chromatically. So a 0 is a C, a 1 is a C sharp, a 2 is a D, a 3 is a D sharp, and so on, up to a 11 is a B. And so values 12 through 15 here have no meaning. It's just chromatically all the notes within that one octave. So that is what each of the note commands signifies. And this allows, like I said, for playing grace notes, rests, and some really fun stuff, even with no further instructions. The other instructions are set immediate value. First bit is a 1. The next 3 bits are the opcode, in this case 0, 0, 0. The next 3 bits for set immediate are the register number, the number of the register for immediates into which you want to store this immediate value. There are 8 of these registers, R0 through R7, and all they do is store immediate values. And then the next, or the last 9 bits are the immediate value. Okay? And similarly to the store immediate command, there is a store PC command, which has its own bank of registers. The opcode for store PC is 001. And again, it has a register number here, but these are 2 separate sets of registers. So the immediate will go into one register, and then the PC will go into a similarly named register in a separate register file for the PC. The rest of these bits in this instruction have no meaning. They can be set to whatever. Next instruction is a branch not 0, which has an opcode of 0, 1, 0, and then a register number. And what this instruction does is it looks at the immediate register with this number and determines if that register is non-zero, if it's a 1, 2, whatever, it changes the PC of the program to whatever is in the equivalent register in the PC register file and decrements the immediate register. This allows for all types of jumping and repeats in music. If you want to repeat a section and play it a total of 4 times, you could store immediate into R1 of 3, and then store PC into R1, play your music here, and then say branch not 0, R1. So R1 would get 3, R1 would get whatever this PC is, and then we would come down here to the branch not 0 after playing this music, and it would look at R1, see the immediate value is 3, say okay, that's not 0, so it decrements it to 2 and branches straight back to here. Plays through the music again, reaches here, R1 is 2, non-zero, decrements to 1, branches back, plays the music, R1 is non-zero, it's 1 still, so we decrement it to 0, branch back, play the music. Now R1 is 0, so we continue on and play whatever is below this. This also allows, you can store a PC and then branch back to it later to like repeat a section of music out of place. You can play first and second endings. Really, you can get quite creative with just these 3 commands for branching within your program. Then there's 2 more commands that I have. I've got a halt command, which has opcode of 0, 1, 1, with the rest of the bits being meaningless. This command simply tells the machine, okay, I've reached the end of the music, I'm going to stop, and it no longer fetches any more commands or notes after this point. And then the set quarter, the SQ command, which has opcode of 1, 0, 0, and the rest of the bits are an immediate value. This immediate value is read in and used as the quarter note value. So in music, typically, at the beginning of a piece, there will be a notation saying quarter note equals 100 or whatever, and that means that there are 100 quarter notes per minute in this piece of music. If it said quarter note equals 200, you would play twice as fast at a rate of 200 quarter notes per minute. So this allows for changing of tempo during the piece between notes. All notes after this command are played at this new tempo. So that's the complete architecture that the complete instruction set that I invented for this class. Alright, so I'm going to talk a little bit about my assembler here and how it works. So the assembler has some variables. Default file size is 1024, starts at line 0, voice 1, and so on. So all Verilog MIF files, which is the standard format for memory files, must have some information at the beginning, which determines the content of the file and how Verilog reads it. I am printing this out to my standard output right here. All of the information at the top necessary before the instructions start. And then I'm getting a line from standard input. This will continue, for example, if I'm reading input from a file, it'll continue until the end of the file and go through. Unless it's this special command, it will split it into arguments, delimited by spaces. If the first argument is a dash dash, which is a comment, it simply prints out that line as is. Basically, I can put comments in the assembly code file and it will output them to the MIF file, to the bytecode, just as comments and keep them. Else, it gets the opcode from the arguments, prints out the necessary Verilog syntax, and sticks in the entire assembly code as a comment at the end of the line, which is really nice for debugging, and increases the line number. So real quick, if the v2 command is activated, we jump to the end of the file, and then we set the voice to -1 so that right here the voice is decremented every time. This allows me to simply say v2 and then write down the second voice in my assembly code, which has been really helpful. So up here, the interesting function is the getOpcode function, which is right here. The getOpcode function looks at the first argument. If it's a store, for store immediate or store PC, it sets the higher order bit to 1, processes the register number, which is a case statement not a case statement, sorry, it's right here, which just processes the register number and returns the value of it, and then process the value, which says if val is PC, then you're trying to do store PC, so edit the opcode to be that. Else, return the decimal value, the immediate value, here, and it gets added in. Here. For branch not 0, higher order bit is 1, opcode is 010, and it processes the register number. For the halt command, higher order bit is 1, opcode is 011, and there's no more relevant information. Set quarter, higher order bit is 1, opcode is 100, and it processes the immediate value. This is not incredibly robust. You can overload the immediate values and do nasty stuff. You're kind of being trusted not to do that, although I do have some statements up here that help me debug and figure out when I'm giving it bad input for some of the things that I typically mess up, immediate values not being one of those. So if it's none of these for beginnings or first arguments, then it must process the pitch, octave, duration, and volume. Add those together. Those are just the case statements up here, and then it returns that down to here, and that's printed out as a hex number. So how does this thing actually end up working? I give it a file, just a text file like this. Let me look at a couple of instructions. Comment. And then I say set quarter to 160. That's my initial tempo. Store into immediate register 7, value 0. Store into register 6, the PC. This is for calling this section back later after section 6 of the music. Then at the beginning of section 1, I store R01 and I store R0 PC. And then I play the notes. Notes are encoded in my assembly as note name, octave, duration in 16th, quarter, eighth, half, whole, SQEHW, and then the volume, pianissimo, mezzo, whatever. And for example, a rest is a volume of R. SE right here means 16th note plus 8th note. You can put whatever values you want there and it'll add them up for you. So it plays through the first section here, repeating this one measure. So it stores 1 in R1, stores the PC in the equivalent register, and then branches so it repeats it once. Comes down here, repeats the entire first section, plays the second section, and so on. And then way down here I've played the entire first voice. So I say halt to end the first voice, V2, set quarter to 160 because that one also plays at 160. And then I enter all of the commands for the second voice and it will encode them for me all the way down to the end. So I can come over here once I've compiled my assembler, which is kind of ironic, and run it. I can take the input from a text file and output it to a .mif file. And then let's see what's in that MIF file. It gives me all the Verilog necessary to run it. And it even gives me the input up here I need, the syntax context, so that I can take this MIF file and just drag and drop it into my project and compile, and it will run no further alterations necessary at all, which has been incredibly helpful as I've been putting this piece together. And then it'll play through counting up for voice 1 and then reaching the end and counting down from 10:23 for voice 2. Really awesome thing that happened with this piece of music is that voice 1 has 567 commands, so 568 is a halt, and then voice 2 starts at 10:23, runs down, 569 is the last note, and so 568 is the halt again. So I have one halt in the middle of my program that halts both voices. The fact that both voices took up exactly 1023 commands, leaving one for that halt, was really kind of cool. So I'm not going to talk about the Verilog too much for this project. That ended up being about at least half of my working time just assembling the Verilog, probably more, but it's fairly standard for most of what we've been doing in this class, especially the branches and non-note commands. You can imagine how those are encoded, because that's what we've been doing all semester, which was amazing to show me how much I've actually learned this semester when I got around to doing those. So that was pretty cool. One thing I will talk about with the notes is calculating the frequency. So general formula for the frequency of a note is that it's equal to some base frequency, F0, times a value A raised to the nth power, where A is equal to the 12th root of 2, and N is equal to the number of half steps away that your note is from this base note F0. Now, Verilog can't, or Quartus and the FPGA board can't really calculate 12th root of 2 raised to the nth power. in real time with the frequency clock ticking and stuff. So I had to improvise, or simplify, rather. So the first thing I tried to do was make a table of frequencies for every single note I had, which really ended up not working because I have 8 octaves times 12 notes is 92 values, and Verilog kind of stuck its tongue out at me when I tried to put those in there. Thank you to Kathy for helping me find that bug, figuring out what was actually going wrong there. So I ended up changing that logic. What I'm now doing is I'm storing frequency for 12 notes, C0 through B0, all of the bass octave notes. So that I'm only storing 12 values, which Verilog is perfectly happy with, and each of those values, C0 through B0, is stored. And whenever I have a note, I go to the bass note corresponding to that note. So if I'm playing an F, I go to F0. And therefore, I am a multiple of 12 half steps away. So N is essentially going to be, in this case, the number of octaves away. If I'm 2 octaves away, that's 24 half steps. So I have, sorry, N is not number of octaves. It simplifies the number of octaves. 12 over 2 raised to the 24th power, but these cancel, and now I am raised simply 2 raised to the 2nd power. So this weird, yucky, ugly, horrible calculation simply evaluates to 2 raised to number of octaves away that I am. So I simplified it to being that. And then so this becomes bass frequency times 2 raised to the octaves. But 2 raised to a power is simply a bit shift. So to make it faster to calculate, the line has become this, which getting to this one line was probably 5 or 6 hours of work, and it's the line in my program that I am most proud of. So I thought I would show you that. Once you have the frequency, you just set a clock ticking to flip the sound wave over however many times per second. You add the 2 sound waves together for 2 voices. Stick that to the output. Thank you to Andrew for showing me how to put output to the board once I had the frequency and the correct wave and stuff. That was really also instrumental to getting my project working. So that's a quick overview of what actually is going on inside the Verilog code. So that's it for talking about the code in this project. I've really learned a lot this semester. It's been incredible. So thank you to Professor Geith. And if you're considering taking this class, make sure you have the time for it because the workload is high, but the payoff matches the workload. You will learn a lot. All of my code is up on GitHub. There's a link down below in the description. As of this filming, I've only got one piece of music input, but likely I will be still obsessed with this project over the Christmas break, and I will input more pieces. They will go up on the GitHub as that happens. So take a look at the code if you want to see what it looks like behind the scenes of this project. And here's the one piece of music that took probably 8 to 10 hours to input. It's got a lot of repeats and other fancy little things, brace notes and whatnot, because I wanted to test the limits of all my commands and have something that I could really show off. So here you go. By the way, there is also a link to a better version of this piece played by actual musicians in the description. Enjoy!